Hello everybody. In this video we're going to start a new topic which is a very important topic, and actually we use Matlab a lot for this purpose, which is the integration. I'm not going to talk about the process in Matlab, but I just want to give an introduction which I believe is an important introduction for chemical engineers to understand. It's not only the mathematical background or why we have the equations or how we do the calculations and everything. I want to go a step further by talking about why we see this kind of equations, which is the differential equations, and what is the purpose of using these equations and how we deal with this kind of equations. While we were working with Matlab, since we started till the last video that we were showing before, we were talking about algebraic equations. So we solved equations either by using matrices or by using f-solve or whatever the way we solved the equations, or even there were a set of equations we used the f-solve or the methods that we use to do the solution. All of them were using algebraic equations, so we didn't deal with any differential equations. To understand first what is the differential equation, it is any equation that contains the differential term, which is d by dx, d by dt, whatever. This is what makes the equation differential. And to understand the difference between the algebraic and differential equation, I would like to give this with a chemical engineering example, and why do we see this differential term, and why we see other equations that do not contain this differential term. I would just go through kind of some modeling concepts, which is the types of systems. So in our engineering applications, we deal with two types of systems. The first is what we call the lumped parameter system, and the other is the distributed parameter system. And the just to give you an example of the two or these two types of equations, I would give a very famous and simple example, which is two types of reactors. The what we call the CSTR, which is the continuous stirred tank reactor. And this reactor is kind of very simple reactor. Actually, we have here some assumptions that make the reactor very simple to model. And these assumptions is that I have this is a tank, and this is the feed, which has the flow rate Q and the concentration Ci, for instance, and there is the effluent from the reactor, which has the flow rate Q and the concentration C out, and we assume that there is a mixer that mixes everything inside the reactor very well, so that you have the concentration homogeneous in every point on this reactor. And that's why the equation is simple. Assuming that you have a first order equation, for instance, reaction, for instance, then you would have you would do kind of simple material balance equation. You would say that the flow rate in minus out equals the reacted, assuming steady state, so we don't have any d by dt term. What we have in is Q Ci, assuming that this Ci is the reactant which is getting consumed. So it's gonna be Q C out plus K multiplied by C multiplied by V. Here this C should be the Cn, because the reaction takes place inside the reactor, but actually we assume that this is exactly as this, so it's gonna be C out. So the final equation would be Q Ci minus C out equals K C out multiplied by V, which is kind of very simple equation. It's simple algebraic equation, so we don't worry much about solving this equation. And the other example for the distributed parameter system is what we call the PFR, which is the plug flow reactor. So the plug flow reactor is a different type of reactor. You have here, so it's kind of tubular reactor. You have the feed, which is going with the flow rate Q and the concentration Cn, and it passes by this tube which contains the catalyst or whatever thing you have inside, and then you would end up with the product which has Q and C out. Here we cannot use the same assumptions that we used in the previous case, because here we assumed perfect mixing, we assumed homogeneous concentration, but here we cannot do that because in every point of the reactor you have the concentration changing. So you cannot assume that the concentration here equals here, and that's why I cannot use this kind of equation. So what we do is that we take a very simple differential part of the reactor with thickness dz, assuming of course this is steady state, and assuming that we have constant diameter and other assumptions to make the process simple. And when we do our calculations, we do the calculations on this small part, assuming that it's very small, so that we can assume that this small part is a mini lumped parameter system, and we can do these calculations on this small part. So we have here C I, and this is, or just make it C, and this is C plus DZ, or DC, I'm sorry. And then we would do our calculations, which is the same. We have here the C, the Q multiplied C, which is the N, equals the out Q multiplied by C plus DC or minus DC, whatever thing. Let's make it minus because this is a consumed material. And then we have here the reactor, which is the consumed by reactor, which is gonna be R, it's K multiplied by C multiplied by the volume, and this is the differential volume in this case, so this is gonna be A dz. So we can now cancel, this will cancel out, and then we will end up with something like this: dc by dz equals kCa. So this is the equation that we will end up using, which is a differential equation. And and this is the point that I want to point out, is that for this lumped parameter system we didn't have any parameter that is changing with any independent parameter like time, like space, whatever. But and that's why the equation came up as an algebraic equation. However, here we had this equation, it was a differential equation because it describes a differential process, and this process we have a dependent variable, which is concentration, which is dependent on another independent variable, which is the space or the length of the reactor. And that's why the equation came as a differential equation. So it's important, even before you go on and start to model the equation or the system or write the equation, you need to understand that this must be a differential equation. It must be described as by a differential equation, and this must be described by an algebraic equation, of course assuming that this is steady state. If this is not steady state, you will have a dc by dt term, which we will not talk about in this video. So the concept is important. So now comes the question. I know well how to deal with this type of equation, but I do not know how to deal with this. I cannot substitute in this equation. And here comes the point that we want to make in this video, is how to deal with differential equations. This is a very important point, how to deal with differential equations. And to deal with differential equations, you have one of two paths. And these two paths is, first, to use what we call the analytical solution. Okay, and the other what we call the numerical solution. Okay, to understand the difference, the analytical solution, you can predict what you are gonna do in the analytical solution from its name. The analytical solution means that you do some analysis to the equation, and what we do is that we convert the equation from a differential equation into an algebraic equation. And this is what we learned in high school and in the first 1 or 2 years in the math classes in college, is how to do the integration. And for instance, if I have the integration of x squared dx, then this is gonna be, for instance, if it the x squared dx by dt equals t. For instance, if this is an equation, it's x squared dx by dt equals t. If this is an equation, you can simply tell that I will separate the variables. I would put this here, and this is gonna be x squared dx, and integrate this, and this is gonna be t dt, and integrate this, and then this is gonna be x power 3 divided 3 equals t power 2 divided 2 plus constant. And then you need to have what we call the initial condition or the boundary condition, depending on the type of the condition, which tells you at time equals whatever you have, x equals whatever, you can then substitute and then get the value of c, and then you have the solution done. And what we see, that we started here with a differential equation and we ended up with an algebraic equation. The good thing about this is that this is a general solution, which is a very important point. This is a general solution, which means that the solution is applicable for any kind or any values that you can substitute in. So you do this solution only once, and then you forget anything about this equation, and you deal with this algebraic equation simply without any issues. You can put any value of x, any value of t, whatever the value you put, the equation is going to work. So you are done with the differentiation. You don't deal with any form of the differential equation anymore. But this is not always available, this analytical solution. And of course, you know that this is a very tedious process, and the integration is not an easy thing. And there are types of equations that would take time, long time to get a solution, and this might end up with a very complex equation actually. And that's why for some equations we don't know how to get an analytical solution, or if the analytical solution is very difficult, you can go for what we call the numerical solution. And for the numerical solution, we actually do what happens actually in the system, which means that I start with the initial conditions. I know the C, the feed. I know all the information about this stream going in, and I go step by step. I define the step, which is kind of this DZ. I define this step, and using the calculations, you can calculate the concentration on the next step. From the next step, you can calculate the concentration on the next step, and then go one by one until you reach the end of the length of the reactor. There are different methods that you can use to do this, and I believe most of the audiences will be familiar with this kind of equations, like Runge-Kutta, like Euler, and there are other equations. But the point here is that this is the good thing about this solution is that it works for any kind of equation. You don't worry about getting an analytical solution for this, whether there is a solution or not. You don't worry about this. You just plug the equation and do the calculations, and it doesn't matter how the equation looks like. But the problem is that you do a lot of calculations. For instance, for large Runge-Kutta equation, you have to calculate 6Ks or 4Ks for each step of these. So you calculate like 4 parameters and then get the average and do kind of long equation or calculations so that you can get this concentration here, and then the second, and then the third. So it's a very time consuming process. And if you're solving this by hand, then you would think about it many times before taking this step and deciding to go for the analytical solution. Now with the presence of the computers and all these tools that can do the computations easily and quickly, you don't worry about this. This can be done in a split of a second, and this is what we'll see in Matlab. But it's important for me to make sure that everyone understands this concept, and that we have two types of solutions. This works for some cases and this works for other cases. Sometimes this is better, sometimes this is better, and it's your choice at the end of the day. And the goal is to get a solution for this equation. So the clever person would know how to pick the right equation, which or the right way of solution that will work better for his case. So this is what I have here in these first 2 or 3 pages of the notes. This is the introduction, and in the next videos we will talk about the analytical integration, and this is the section 9.2, and we will see some functions that do this analytical integration, and then we will go for the numerical integration and see some methods like the getting the area under the curve and using the tabulated data or whatever the methods. So this is gonna be the topic of the next videos. So I'll see you then, inshallah. Goodbye.